Ever wonder what's happening deep beneath your feet? It's not just solid rock. Down there, an incredible fiery dance is constantly reshaping our planet. Molten rock, or magma, is being born, moving, and transforming in a hidden world of immense heat and pressure. This is the heart of Earth's engine, creating everything from explosive volcanoes to glittering granite mountains. At the same time, existing rocks are being squeezed, cooked, and twisted into entirely new forms without even melting. Imagine a simple piece of shale being crushed under the weight of a mountain range until it turns into a shiny, layered slate or even a banded gneiss. These are magmatic and metamorphic processes, the two powerhouse forces in the rock cycle. Today, we're going on a journey to the center of the Earth metaphorically, of course, to uncover these hidden secrets. We'll explore how magma is made, how it builds new land, and how solid rock can transform into something completely different. This isn't just a geology lesson. It's the ultimate guide to the planet's amazing, unseen construction site. So, if you're ready to have your mind blown by the sheer power of our world, stick around. Let's start with the fiery heart of it all, magmatic processes. Simply put, these are all the activities related to magma, from its birth to its final solid form as igneous rock. Magma is molten rock that originates in Earth's mantle and lower crust. It's the lifeblood of our planet's crustal growth and the fuel for every volcano. But where does this molten rock actually come from? It's not like there's a giant ocean of lava under us. Magma forms when solid rock in the mantle or crust starts to melt. This can happen in a few ways. First, you can just crank up the heat. If rock gets hot enough, it melts. Second, you can decrease the pressure. This is called decompression melting. Think of it like taking the lid off a pressure cooker. The drop in pressure allows melting to happen at lower temperatures. This is what occurs at mid-ocean ridges, where tectonic plates pull apart. Third, you can add water or other volatiles. Adding water to hot rock is like adding salt to ice. It drastically lowers the melting point. This is a key process at subduction zones, where one tectonic plate dives beneath another, carrying water down with it. Lastly, heat can be transferred from an existing body of rising magma, melting the rock around it. These conditions are most common at mid-ocean ridges, subduction zones, hotspots like Hawaii, and continental rift zones where the land is being torn apart. Once magma is formed, it doesn't just sit there. It begins a complex journey. First up is partial melting. Rocks are made of different minerals, and each mineral melts at a different temperature. So, as a rock heats up, only certain minerals will melt first, creating a magma that has a different chemical composition than the original parent rock. Because this new magma is less dense than the surrounding solid rock, it starts to rise. This ascent isn't always a smooth ride. Magma can force its way up through cracks and fractures in the crust. As it moves, it continues to evolve. One major process is called fractional crystallization. Just as minerals melt at different temperatures, they also crystallize at different temperatures. As magma cools, the minerals with the highest melting points will crystallize first and sink, changing the composition of the remaining liquid magma. The magma can also assimilate, or melt and incorporate, the surrounding country rock it passes through, further altering its chemistry. Sometimes, two different magma chambers can connect, and their magmas will mix, creating a hybrid composition. Finally, after all this movement and change, the magma will cool down and solidify, a process called crystallization. This is the final step that creates igneous rocks. The rocks formed from these processes fall into two main categories based on where they cool. If magma cools slowly, deep within the Earth's crust, it forms intrusive or plutonic igneous rocks. This slow cooling allows large, coarse mineral grains to grow, which you can easily see with the naked eye. Classic examples include granite, diorite, and gabbro. These rocks make up the core of many mountain ranges, exposed only after millions of years of erosion. They form massive underground structures like batholiths, which are huge collections of plutons, or can be injected into existing rock layers as sills, which run parallel to the layers and dikes, which cut across them. On the other hand, if magma erupts onto the surface as lava, it cools very quickly. This rapid cooling doesn't give large crystals time to form,
resulting in fine-grained or even glassy textures.
These are called extrusive or volcanic igneous rocks.
Think of basalt, the dark rock that forms the ocean floor. Rhyolite, its lighter-colored continental cousin. Pumice, the frothy rock so light it can float. And obsidian, which is natural volcanic glass.
These rocks are formed in dramatic fashion at volcanoes, in lava flows, and from explosive pyroclastic deposits.
So, from the hidden depths to explosive surface eruptions, magmatic processes are constantly creating new rock and shaping our world's landscapes.
Now, let's switch gears from the fiery creation of new rock to the incredible transformation of existing rock. This is the world of metamorphic processes. Metamorphism literally means to change form. It's the solid-state transformation of a pre-existing rock called the protolith into a new type of rock. The protolith can be igneous, sedimentary, or even an older metamorphic rock. The key here is solid state. The rock gets hot and is put under immense pressure, but it never actually melts. If it melted, it would become magma and form an igneous rock. Instead, it changes its texture and mineralogy while remaining solid. What causes this incredible change? The main drivers are heat, pressure, and chemically active fluids. Temperature can increase due to deep burial in the Earth's crust or from being baked by a nearby magma intrusion. Pressure increases with depth or from the immense compressional forces during mountain building events where tectonic plates collide. Hydrothermal fluids, which are hot, water-rich fluids, can also circulate through a rock, changing its chemical composition. Finally, the directed stress and shearing during tectonic activity can deform and realign minerals within the rock. Let's look at the specific changes that happen during metamorphism. One of the most basic is recrystallization. The existing mineral grains in the rock don't change their chemical composition, but they tend to grow larger or change their shape. Think of tiny clay particles in shale recrystallizing into larger, visible mica flakes in schist. A more complex process is neomineralization, where new minerals are formed that are stable under the new temperature and pressure conditions. The old minerals break down, and their atoms recombine to form entirely new ones, like garnet or staurolite, which are classic metamorphic minerals. One of the most defining features of metamorphism is the development of foliation. This happens when the rock is subjected to directed pressure or stress. Platy or elongated minerals, like micas, align themselves perpendicular to the direction of the stress, creating a layered or banded appearance. This gives us textures like the slaty cleavage in slate, the schistosity in schist, and the distinct banding in gneiss. Lastly, there's metasomatism. This is when hot fluids introduce new chemical elements into the rock or remove existing ones, fundamentally altering the rock's overall composition. Metamorphism isn't a one-size-fits-all process. There are several different types, depending on the geological setting. The first is contact metamorphism. This occurs when rock is heated by a nearby magma body. The heat bakes the surrounding country rock, causing recrystallization. Because directed pressure isn't the main agent, these rocks are typically non-foliated. A great example is marble, which is metamorphosed limestone. Next is regional metamorphism. This is the big one. It affects huge areas and is associated with major tectonic events like mountain building. It involves both high heat and high pressure, resulting in intensely deformed and foliated rocks like slate, schist, and gneiss. Hydrothermal metamorphism happens when hot, chemically active fluids circulate through rock, typically near mid-ocean ridges. This process alters the rock's mineralogy, a key process in forming certain ore deposits. Finally, dynamic metamorphism is caused by intense stress and shearing along fault zones. It doesn't require high temperatures but mechanically grinds and crushes the rock, creating rocks like fault breccia and myelinite. The type and grade of a metamorphic rock tells a story. We can look at the minerals present, called index minerals, to determine the temperature and pressure the rock experienced. Geologists can even chart a rock's journey through different pressure-temperature conditions, known as its metamorphic facies. Low-grade rocks like slate and phyllite form under lower temperatures, while medium-grade schist and high-grade gneiss and magmatite form under progressively more intense conditions.
So let's put it all together and compare these two powerful planetary engines.
The most fundamental difference is their origin.
Magmatic processes start with melting rock to create magma. Metamorphic processes alter solid rock without melting it. Their primary agents also differ. For magmatic processes, it's all about the conditions that generate melt, heat, pressure changes, and volatiles.
For metamorphic processes, the agents are heat, pressure, and fluids that modify an already solid rock. This leads to very different end products.
Magmatic processes create igneous rocks, either intrusive like granite or extrusive like basalt.
Metamorphic processes create metamorphic rocks,
which can be foliated like schist or non-foliated like marble.
Their textures tell different stories too. In igneous rocks, grain size is mainly controlled by the cooling rate. Slow cooling means large grains. Fast cooling means small grains. In metamorphic rocks, the defining texture is often foliation, the alignment of minerals caused by directed stress.
Their geological settings are also distinct. Magmatic activity is concentrated at volcanoes, mid-ocean ridges, and subduction zones.
Metamorphism is dominant in the cores of mountain ranges, deep in the crust, and in the baked zones around magma intrusions. Finally, they play different, but equally vital, roles in the rock cycle. Magmatic processes create brand new crust from the mantle.
Metamorphic processes recycle and modify existing crust, preparing it for either uplift and erosion or for eventual melting to begin the cycle anew.
Together, magmatic and metamorphic processes form a continuous dynamic loop that has shaped our planet for billions of years. They build continents, create mountains, fuel volcanoes, and forge the very ground we stand on.
Understanding them is key to understanding Earth's history, its present, and even its future.
From the fiery birth of magma deep in the mantle to the slow, powerful squeezing of rock in the heart of a mountain, these hidden forces are a constant reminder of the incredible power at work within our planet.
I hope this deep dive has given you a new appreciation for the rocks around you and the epic stories they have to tell. Next time you see a granite countertop or a slate roof, you'll know the incredible journey that rock has been on. Thanks so much for watching.
If you found this guide helpful, please give it a thumbs up. And don't forget to subscribe for more deep dives into the wonders of our world. See you in the next video.